Okay, so let's now solve a vertical spring problem. So here we have a spring, we hang a 15 kilogram mass on it, and it reaches equilibrium. At the equilibrium point, the upwards elastic force, Kx, is balanced by the downwards gravitational force, mg. So if we write a force equation, sum of the forces will equal Kx subtract mg will equal 0. So this equation can be solved then to find the equilibrium stretch of the spring. If we do the algebra, rearrange it a bit, we get x equals mg over k. Now that is going to be 15 g's over 450, should be a little bit less than a third, so 0.327. So that's the equilibrium stretch of the spring. It's the distance x. And on our diagram, that's the stretch from here down to the equilibrium point. So it's stretched 32.7 centimeters from there to there. All right, so now let's consider taking that mass, pulling it 20 centimeters below equilibrium. So from there to there is another 0.2 meters, and then we let it go from there. Then we want to write the energy equation to find the speed it has when it's back here at the equilibrium point, and when it's 5 centimeters above equilibrium, so about right there, we're also interested in how fast it's going. Alright, so mechanical energy will be conserved once again. So the energy at the release point will equal the energy when it's back at equilibrium, will equal the energy when it's 5 centimeters above. Now in all cases, we're going to have spring energy, gravitational energy, and kinetic energy to consider. So that's spring energy, gravitational energy, and kinetic. At the release point, it's going to start off at rest, so there's no kinetic energy. Let's call this our zero of height here. So that means there's no gravitational energy to worry about at that point either. Therefore, the only energy is elastic energy. So 1/2 kx squared elastic energy at release. How much is the spring stretched at that point? Well, 32.7 centimeters to reach equilibrium, another 0.2 beyond. So it's stretched 52.7 centimeters. 0.527 meters. That's the initial energy. Okay, comes back to equilibrium right here. It's moving, so it's got kinetic energy. And the speed, well, that's our unknown. Back at equilibrium, well, it's got some height. Relative to this zero, it's got a height of 20 centimeters. So we're going to add mgh, and the h is 20 centimeters, or 0.2 meters. It also has elastic energy. How much is the spring stretched at this point? Well, it's exactly the 32.7 centimeters that we calculated over there for equilibrium. So 1/2 kx squared, where the x works out to be 0.327. Now, when it's 5 centimeters above equilibrium, it's again going to have all three forms of this energy. There'll be kinetic energy, there will be gravitational energy, there will be elastic energy. So, how much do we have of these? Well, once again, the speed is the unknown. That's what we're trying to find. What's the height? Well, if this is 0, it's 20 centimeters to reach equilibrium, and then we're 5 centimeters above. So that is 25 centimeters of height, 0.25. What's the spring stretch? Well, it was 32.7 centimeters to reach equilibrium, but we're now 5 centimeters above equilibrium. So 5 centimeters less than this is 27.7 centimeters. 0.277 meters. So, definitely complicated, but it just requires a bit of attention to detail. And a good diagram is helpful too. Next, so again, vertical spring, we let the mass come to equilibrium. So once again, the equilibrium equation will just be an equation of balanced forces, which says that the kx force is exactly balanced by the mg force. Sum of the forces will equal kx subtract mg will equal 0 because it's at rest at the equilibrium point. And solving for x again, we'll get mg over k. And let's just quickly calculate that. So that's going to be 25 g's over 800, which is 30.6 centimeters, or 0.306 meters. So that means that from the end of the spring, it is 30.6 centimeters to the equilibrium point. Okay, so what are we told? Okay, we're told that the mass is a certain distance. It's 18 centimeters above the equilibrium point. So from there to there is 0.18 meters. Okay, and it's moving. It's got kinetic energy, and clearly the spring stretched. So it's going to have all three forms of mechanical energy at that point. And we want to find the maximum stretch of the spring. So let's just draw a diagram for that. Way down here, the mass is going to reach its maximum stretch, and at that point, it will be stopped. Makes sense to set this as the zero of height. And that means when it's down at the bottom, it's got no kinetic energy. That says V equals 0. It's a bit sloppy, but V equals 0. Because it's at rest, no kinetic energy, 0 of height, therefore no gravitational energy. So the only thing we have to deal with there is the elastic energy. So let's use a variable here. Let's call this x. Okay, that's the total stretch of the spring at that lower point. So let's write the energy equation. So the energy at the start, okay, energy at the start. Okay, just give me a second here. So the energy at the start, there we are, we're back in business now. Will equal the energy when it stops down at the bottom. Alright, so we said that at the start, it's got kinetic energy, half mv squared. It's got gravitational energy, mgh. And it's got elastic energy, 1/2 kx squared. The speed is given, 5 meters per second. For the height, well, we'll have to work a little bit at that. This variable's x. We would subtract 30.6 centimeters to get to there, and then we have to add 18 centimeters. So basically, it's going to be x minus 10.6 centimeters to reach this point. Okay? 12.6 centimeters. Because 12.6 is just the difference between the 30.6 centimeters from there to there and the 18 from there to there. So the height is x minus 12.6. And the spring stretch at this point is 30.6 minus 0.18. That's just the 12.6 centimeters, or the 0.126 meters. Alright, so that was the energy at release. Now, the energy at the bottom very straightforward. There's no kinetic, there's no potential. It's just elastic energy, 1/2 kx squared, where this is the unknown that we called x. So there's the energy equation that you would solve to find x. Now, it's going to be quadratic in x. It's not going to be very pretty, but there you have it. It's doable. Okay? So we had to be a little bit careful here with getting the correct expression for the height. Just maybe to elaborate a tiny little bit on that, where that comes from, just to make sure it's clear to you. This is x minus the 0.306, that's the height of the equilibrium point, plus 0.18 above the equilibrium point. That's how we arrive at this expression here. Now that answers, that's the energy equation for 6b. We're not going to do 6c. It's similar in difficulty to this, so I think you should be able to handle that one. And hopefully this brief video helps you with understanding how to make these equations for a vertical spring.